Thank you, Howard. So yeah, I'm Billy Kozma here at NTIA, working in the theory division specifically on propagation, and we're going to do a real brief kind of overview as to active areas of research that are going on within the field of prop model here at ITS. It's only about 10-minute overview, so we're just going to kind of sample the buffet of things that are happening. We're not going to take questions, but if you do have them, either reach out directly to my email address there or put them in the chat, and either I'll try to respond maybe later or we'll pick them up maybe in the panel that follows. So with that, next slide. So yeah, one place I want to start is really two of the key models that are being at ITS that we've had and have been around for decades is the irregular terrain model, ITM, or the air-to-ground model, IS-77. Many of you are familiar with these and have used them yourself. Other of you may not be as familiar, but if you've used any sort of software to do, interference analysis or any of the, commercial packages, likely this is one of the models that are being used under the hood when you're working to do those sorts of work. So you may have, even if you're not familiar with it, you probably have used these models unknowingly in the past. They've been around, they're general purpose models. Both are really founded on technical theory. They're based on electromagnetic theory and first principles. They build out from there, and then at the end, they kind of layer on statistical analysis based on a large set of measurement data to deal with things like time variability and location variability. When we're talking about these things, having just median predictions isn't enough, especially when we're doing interference analysis. We're trying to think about coexistence between systems. You need that layer of statistical distribution on top of that. And so these are well established, used across the government and commercial industry for those types of work. Recently, they were originally established back in the 60s and the 70s in their work, and there hasn't been a lot of work improving those up to date. Of course, today now we're dealing with sharing scenarios and modeling scenarios that are quite different than what was originally looked at. Doesn't mean they're not applicable, but that does mean there are rooms for improvement. And so we are looking right now, in the past couple of years, we've been throwing more resources at adding improvements and iterating on these, specifically these two models, to push out some more additional improvements to the community to get that. So one of the areas within ITM, so ITM is a terrestrial model. It does both point-to-point analysis and an area mode analysis where you don't necessarily know exactly where it is. It's more applicable for maybe a Monte Carlo distribution or something like that. Is we're aware that within a line of sight link that there are some weaknesses in parts of the model depending on where it's applied. And if you think about a sharing scenario, especially if you're sharing with a radar that's far away, those line of sight links can really be the long pole in the tent, especially, that interference from, say, a base station into a radar line of sight. Having an accurate representation of what that loss is can be really important, can really dominate whether, where those exclusion zone boundaries are or coordination zone boundaries. And so over the past year, we've had some folks within ITS really looking at that more closely and trying to work at better ways to kind of improve that line of sight geometry within the ITM model. Within the past couple of months, they've arrived at some preliminary algorithms that show within a specific sorts of geometries an up to 10 to 15 dB improvement. And that's really big. I'm sure you guys all are aware. Now, it's not general across all scenarios that are line of sight. And so right now they're looking at both generalizing that, how it applies to all different types of line of sight geometries, as well as proposing, we're going to throw some resources doing some measurement data as well. So historically, right now we've been using the historical measurement data, phase 1 and phase 2 that's hosted on ITS website. And so we're going to be taking some additional measurement data to really validate it and hopefully, in the upcoming years here, push out some improvements to the modeling that are really going to be useful. Likewise, in the air-to-ground model, it's built on the same foundation, TechNote 101, as ITM, but obviously it captures specifically the atmospherics that are involved in air-to-ground link. And much like ITM, it's limited to 20 gigahertz because as you go up, in particular for air-to-ground links, what that atmospheric effects are, they become really important, especially when you're talking about the absorption of water vapor and oxygen. And so we're currently working on modernizing MPM 93, which is the millimeter wave propagation model that is able to capture that line-by-line summation of water vapor and oxygen within the atmosphere, how it affects both bending and the absorption of those molecules. And so we're looking at both modernizing MPM 93 and pushing that into IF77 so we can extend the upper limit of both ITM and IF77 to cover millimeter waves and support these new scenarios that we're looking at. And lastly, something that, this, I think, and I'll touch on this, explain in a future slide here, we recently published a report on tropospheric forward scatter that rederives the first principles of troposcatter that was used in the development of these models. So if you look at some of the citations, some of them are unpublished works. We had an engineer or a mathematician rederive that from first principles, publish that, and that's going to lay the foundation to some upcoming troposcatter measurements that we're going to be doing and modeling improvements. Next slide. Another area, obviously, is quite large in the news nowadays is millimeter wave propagation. March of last year, we conducted some measurements at 37 gigahertz. We developed a new measurement system to do this. These were mobile measurements. We drove through downtown Boulder. We captured those results. We did some initial validation with 3GPP models, but non-line of sight and line of sight types of scenarios. We compared that with environmental information, such as 3D LiDAR data. They didn't always agree. We had some hypotheses as why they might, and we did kind of propose some additional measurement scenarios. We're looking at performing some additional measurement scenarios winter of next year because the measurements were originally taken without foliage and the leaves weren't out on the trees yet. We want to make sure that when we do a second set of measurements, we're in the same, the environment has the same characteristics that we originally did when we captured those. So we're hoping here in winter next year to do some additional measurements at 37 gigahertz, maybe rolling this into a publication and improving some modeling efforts within the millimeter wave band. Next slide. So another real big program that's just kicking off this year, fiscal year, is a mid-band propagation model initiative here that's funded by the DoD. It's ranges from 3.1 to 4.2 gigahertz. And really, everything is in play. We're looking at link geometries, both air to ground, talking about clutter, but also long-distance diffraction and troposcatter links. And so really, we're trying to this is a large program, multi-year, where we're going to be funding, or we're going to be really focusing on specifically at 3.5 band, but really broadly, 3.1 to 4.2. So we're going to be engaging with the community to do kind of a community-driven modeling approach, which is something we're going to talk about in a panel coming up. We've been rolling out a new measurement system. So we developed a new clutter measurement system that not only has a lower noise floor than our previous one that we've used, but also incorporates some high fidelity geolocation system so that you don't have GPS drift when you go through dense urban areas or underneath tree canopies. So that's going to be rolled out. We're going to be doing diffraction measurements, and we're actually setting up some long distance troposcatter links to collect data to basically validate some of that troposcatter research, that model I talked about, the development previously, and possibly make some improvements there, dealing with some atmospherics, experts in the kind of atmospheric world from NOAA and other agencies. So it's a really quite big effort, and it really covers a whole of prop modeling there. Next slide. And lastly, of course, we're doing a lot of work in clutter modeling, not just in the 3.5 band, but also more broadly. We've been building on work that we've been done with AWS-3 at 1.7 gigahertz. Again, we're expanding this to mid-frequencies, and really we're combining electromagnetic theory, measurement data, both that we have and that we're going to be capturing, as well as environmental data when it comes to terrain, structural, or vegetative that you can capture from LiDAR. And how can we incorporate all this data that we have to really improve modeling as a whole, both on a point-to-point and also statistically based, right? So getting those distributions of location variability and time variability that are really important when we start to talk and think about how you manage interference, some of the topics the previous panel talked about. And so these things are going to be rolling into clutter modeling, updates to IF77 and ITM. As you know, those don't have clutter effects at the current time. And so we're really trying to feed this all through. And also there's going to be an open data component of this. And then last slide. And then just real quick so we can get into the panel. Everything I talked about now, you can imagine this is going into publications as we disseminate this information and things are worked. But a lot of you, while that's great and you're really interested in the mathematics and the theory, there's a sizable chunk of you in the community that you're working at a different level when you kind of deal with these models, where you want to be able to do analysis or run simulations. And what you want is not necessarily the gory details of how the models work, but you want the confidence of, I need a model that I can plug into my simulation or my analysis that I know is trusted and someone stands behind it, and then I can solve the problem that I'm really looking at. And so we've rolled out PropLib, the ITS propagation library. We're open sourcing model codes on GitHub as a way to engage. We're issuing releases that are both code signed, so they're authoritative and came validated and tested by ITS. We're looking to engage community. If you find bugs, file an issue. We can start up a conversation, and we can iterate this in an open, transparent manner. And so we have a bunch of models in development or that'll soon be going public. And actually, later this summer, we're going to be rolling out support for Linux and cross-platform Python packages. So, I encourage, if you're at that level, check out that GitHub link, engage us through that. And I think it'd be a really nice place where maybe you're interested in what's being done at the lower level, but maybe not the details. Here's a way you can kind of plug it into your larger simulations and work with confidence at the results that you're getting out of it. And so with that, let's jump into the panel.